All right, so we're going to look at some more algebraic patterns. So if you haven't already, go ahead and either have access to or print out. We're going to be looking at this number combinations handout, but also the seesaw balances. Okay, that look like this. I think maybe this is a little bit bigger version than what I uploaded. Maybe not. I don't remember if I shrunk them down. But anyway, there should be one full page of number combination on the handout and then 2 of the seesaw balances. Okay, so we're just going to kind of look through those, and I'm going to tell you kind of what I expect for these. These are really just to show you that algebraic patterns can be all different kinds of problems. I mean, they are not cookie cutter by far. And so I just wanted to kind of give you kind of a general taste of what they can look like. So let me zoom in and get a good angle here. Okay, so let's look at the first one. So I purposely picked, you know, some words that were non-words for a reason, okay, so that students don't get really honed in on what the words are, because that's not the important part of this problem. So the first 3 are just kind of mixture problems, really more higher level thinking algebraic problems. I say higher level thinking, it's more elementary school higher level thinking. Okay, so let's look at all of these things. So he has 3 quantities, okay, that he puts in a blender. And then it starts listing all of these things, right? 3 more potatoes than nixes, 2 more nixes than carrots. But then if you get to this part, notice it tells you exactly how many carrots he puts in, right? So we're going to go ahead and list 4 there. Use my pen. I'm not sure that pencil's dark enough. Okay. And then what we can do is we can kind of work backwards, right? If you put in 2 more nixes than carrots, then that would mean there's 6 of these. And then put 3 more potatoes than nixes, so 3 more than that would be 9. And then the total's pretty easy, right? We just add up the list. Okay. So sometimes things that may look a little difficult actually aren't that challenging at all. Same kind of thing for 2 and 3. So let's go ahead and read it. So we have 1, 2, 3 things. It lists the onions as 4. So and then go backwards. There are 3 times as many lizards as onions. So that means there are 12 lizards. And then he put in 3 less potatoes than lizards. So you'll just make sure you want to read the wording really, really carefully. But if you add all those up, you get 25. Okay, so I think you kind of see the point. So go ahead and pause the video and see if you can do the very last one. This one has a lot bigger numbers, so you'll want to pause the video, take a couple minutes and see if you can do it. So if you pause the video, notice there are 4 eggs, and then if we work backwards, there are 9 times as many apples as eggs. It's a lot of apples. Okay, they're going to be very regular after that, right? And then they're going to do 47 more brims than apples. So if we add 47 to 36, we get 83. And then there are 4 times as many fizits as there were brims, so we'll multiply that by 4. That gives us 332. And then last but not least, 124 more peaches than this, so that is going to be a really large shake, right? A super space shake. If you add all those up, you get 911 items. Okay, the next kind of problem might have more than one answer. We might have, you know, just one answer that makes sense. So you really need to make sure you read. So notice that I say there are 8 balls in a box. Some are red and some are yellow, implying that there can't be 0 of either. Okay, there is at least 1 of each of them. Okay, there are more red balls than there are yellow, and that's supposed to say balls. I think yours will. I'll change it before I upload it. How many balls of each color could be in the box? Okay, so if there's supposed to be more red, that means there cannot be 4 and 4, right? There's supposed to be 8 total. Can't be 4 and 4, so we're going to have maybe 5 and 3. That's an option. But we have to keep red larger than yellow. So we could have 6 and 2, and we could have 7 and 1, but then that would be it, right? We can't go 8 and 0 because there is at least 1 of each color. Okay. Notice these require less equations. You might run into some that need an equation, but for these, I think it probably makes most sense to just kind of figure out the possibilities kind of mentally. So same kind of thing for number 15. We have 17 kites, some pink, some blue. There are fewer pink kites than there are blue, okay, which means the closest they could be and still add up to 17, with blue being higher, is 9 and 8. We could go 10 and 7. We could go 11 and 6. Okay. If you notice a pattern like this, and as long as you've listed a few of them, I'm okay if you use this ... notation, as long as you list the very last one. Notice the last option, if we go up by 1 in this column and go down by 1 in this column, would be 16 and 1. We can't go 17 and 0. Again, there has to be something of everything. Okay. All right, so 6 and 7 are a little bit more thinkers, but, you know, still pretty elementary level. All right, so let's look at this. So there are 8 t-shirts in the box. Again, there can't be none of any color. There are some brown, some purple, some green. There are more purple shirts than brown, okay, and then there are more green shirts than purple. So it looks like brown is the lowest, okay, and then it kind of goes in order here from biggest to smallest, right? There's going to be the most green, this is in the middle, and then the least brown. Okay, so what I like to do is I kind of like to make my independent variable the brown. Notice 1 is the least amount of browns we can have. Okay, and then we can kind of go up from there, right? We could have 2 purple. We can't have 1 purple because it says that there are more purple shirts than brown shirts, not the same quantity. And then notice this would set in stone what this would need to be. Okay, so notice we can also go with 1 brown, 3 purple, and 4 green. Notice that's the last time we could have 1 brown, right? If you think about it, that's not going to work, okay? If you go 1, 4, then that would have to be 3, and then the green shirts would be less than the purple, okay? So we can try a couple more. We can try 2, and then this would have to at least be 3, but then that would have to be 3, right? So actually no numbers bigger than these are going to work, and that's going to be it. All right, and then last but not least, for this one, there are 30 balloons and horns in the box. There are more than twice as many balloons, so I'm going to underline this. They are more than twice. Not twice, but more than twice. As many balloons as horns. How many balloons and how many horns could be in the box? Okay, in other words, I want you to list all the possibilities. Okay. So what I'm going to do is I'm going to first solve the expression that would make it exactly twice. Okay, so if I wanted to kind of set this up, notice this requires a little bit more thought, right? So this is the horns, and this is the balloons. Okay, so notice if I work this out, I get x equals 10. Okay, but this isn't the answer, actually. This would make it exactly twice. And I want to go more than twice. Okay, notice x is the smaller quantity, so x is actually the number of horns. So we can't actually have 10 horns because then we would have 20 balloons and that would be exactly twice. So what we need to do is go lower on the balloons. Notice this would put this at 21. Notice 9 times something a little bit bigger than 2 gives us 21, right? 9 times 2 would be 18, so 9 times 2 point something is 21. And then again, kind of like we did before, we can kind of establish a pattern. So we can keep going down, right? But the very last one we could have would be 1 balloon and 29 horns. Okay, notice in this case the, actually I think that's switched, so sorry about that. Same numbers, just I had them in the wrong columns. Might have even been easier just to mark out the numbers. So, so this should have been 9, 8, 7, all the way down to 1. And then this would be the 21, 22, 23, all the way down to 29. Okay. So notice none of these really needed upper level algebra or anything like that. So let's look at some that might require just a little bit different thought. So let's go ahead and look at the seesaw balances. Let's go ahead and get those out. So we're looking at seesaw 1 and 2. All right, while I'm thinking of it, one thing I wanted to say is I did shrink problems like this down to fit on your homework page. So it is a little small. So if you can't read everything, just know that these instructions right here are for all the Seesaw problems. So you should be able to look at your handout from class if you can't quite read everything on the homework, because I tried to put two side by side. Well, I didn't try, I did. And they're just a little bit small. Okay. All right, so let's look at these seesaws. Okay, so the first thing I want you to notice is that they are balanced. In other words, one side is not lower than the other, right? They're perfectly level, which means that the weight on both sides has to be the same. Okay, so let's read through the kind of rules of these experiments. You have to balance the seesaw. Shapes that are the same have the same weight. Shapes that are different must have different weights. In other words, the circle and the triangle can't have the same weight in this exercise. And then all weights weigh more than 0 pounds. So they all are significant. They're all something. Okay. So let's see if we can kind of break down what we have here and then maybe decide on an independent variable. So one thing we could do is if we wanted to kind of introduce some algebra, we could call, in this case, the hexagons x's, maybe the oval / circles y, and then we'll call the triangle z. So what we have is we know that 2x plus y is balanced or equal to x plus z. So we can kind of simplify this if we want, but we need to remember that the original equation is actually the significant one when we talk about weight. Okay, so we'll go ahead and balance it just to make it nicer, but we need to keep that in mind. So we know that x plus y is going to be equal to z. Okay, so our values are going to be pretty specific here, and it's going to have to work with everything that we want. So what I'm going to do is we're going to write out kind of some thoughts here, and then if we have to kind of eliminate some answers, we will. So let's look at the first one. If the seesaw, the total weight on the seesaw is 12 pounds, so the first thing you need to notice is that means each side is 6. Okay, so there's not going to be a whole lot of ways to get 6 on both sides, especially in staying with the rules. So I like to pick an independent variable. In this case, I probably would pick x as the independent variable, but kind of like the exercises in the last video, you can choose different things as your independent variable. Okay, but I'm going to choose x as my independent variable. We'll put a question mark because it doesn't necessarily have to be x, but I'm going to choose x. All right, so let's just start with it, right? Let's start with the smallest that x would be able to be. Okay, the smallest x would be able to be is 1 because everything has to have a weight of at least 1. Okay, but notice if you set that independent variable, then the y and the z are dependent on that, right? That means that this is 1 and this is 1, so the y would have to be 4. The oval thing is 4. Okay, and then notice if this is 1, that makes this 5. Okay, so that's certainly a possibility. Okay, so now let's work from our independent variable and move on from there. Okay, so what if this was 2? Okay, notice if this is 2, then this also has to be 2. And then if this is 2, this is 4. But notice this breaks one of our rules, right? We can't have 2. So I'm going to say no 2 shapes should be equal. Okay, so sometimes you'll be listing them and you'll realize, hey, that one doesn't actually work. Okay, so let's bump it up to 3. Notice if it's 3, so this would be 3 and 3, that makes this 0. Okay, so we can go ahead and mark that out right now. That can't work. So I'm going to say no 0 weights. Okay, and notice we can stop there at that point, right? Like it's not going to work. Like we already are down to 0 here, so if we bump this one up even higher, that's going to make that an impossibility as far as weight goes. Okay, so it looks like this one only actually had one legitimate answer when we actually thought it all through. Okay, so same pattern, but this time we want the seesaw to weigh 16 pounds, which means that each side is 8. So again, I'm going to keep with x as my independent variable, okay, although I could change if I wanted to. So let's talk about what the smallest thing x can be. So again, x might be 1. So let's slide back up to the picture here. If x is 1, that sets y as 6. So since it's dependent. And then if this is 1, it would make the triangle 7. So that looks like a legit answer. So let's bump up x to 2. If x is 2, we've got 2 and 2 already. That's 4, which makes y need to be 4. And then if this is 2, this one would have to be 6. Okay, so let's bump x up again to 3. So if these are both 3, that means y has to be 2, so that that side can be 8. If this is 3, then z would have to be 5. And then notice if we bump it up to 4, I'm not even going to write it. Notice we're not going to be able to have that, right? 4 and 4 would already be 8, leaving nothing left for y, so that's going to be it. Okay, so you just need to come up with some kind of logic there to figure it out. If you've ever seen on social media, I know some of you have y'all ever seen those problems on Facebook and other things where it's like they have like nonsense pictures where it's like this picture plus this picture equals 30, and then 3 of these equals 5 or something like that, and you have to figure out what all of those are. That's essentially what this is, okay? It's just usually those are kind of meant to trick you, the ones on Facebook. Usually it has to do with, by the way, the ones you find on social media has to do with people not understanding the order of operations. Like they don't understand that they need to multiply before they add. That's almost all of the ones I've seen have been something like that. So maybe take a look next time you see that. Okay, so let's look at this second setup here of seesaw balances. Okay, so we have x, y, and y, and then I'll call this one z. I'm not sure you can really see that, so I'm going to go over it with black and maybe see it, or maybe I'll write above it. I underestimated how dark my printer was going to print this. Okay, so first let's come up with an expression that maybe we can simplify. X plus 2y equals x plus z. And then again, this is the equation we'll need to use, so I'll go ahead and star it. But we're going to go ahead and see if we can simplify it out a little bit. So if we simplify and take out the x, then we know that 2y is going to be equal to z. So in this case, I'm just going to pick z as my independent variable. The reason I'm doing that is because I should have a really easy time coming up with y once I know z. Actually, scratch that. I think I'm going to make y my independent variable. Z would have been just fine, but I'm going to make y my independent variable so that I'm multiplying by 2 instead of dividing by 2. I know it's a really small issue and we can divide by 2 just as easily as we can multiply by 2, but multiplying is usually easier, so I'm going to stick with that. Okay, so let's start with this. Notice we need to figure out what each side would be. So here each side would be half of the 18 pounds, so each side is 9. So let's start here. If this is my independent variable, and again I could have chosen anything, the largest y could be, so last time I started with the smallest y could be, doesn't really matter. You can start with either logic there. But let's start with the largest that y could be. 4 is the largest y could be because we have 2 4s over here and we'd have to have room for something else. Okay, so in other words, if these are 4s, then that makes this a 1. And if that's a 1, that's going to make this an 8. Okay, so notice that's legitimate. That works, right? So let's go down. Okay, it can't be any higher. You can't have 5 and 5. That's already too big, right? We already know each side's only 9. So if you go to 3, you'll get 3, 3, and 3, which means we're already out here. Okay, because no two shapes are equal. So let's keep going. What about 2? Okay, if y is 2, if each of those rectangles are 2, then that would make this x a 5. And if that's a 5, that makes the triangle a 4. Okay, notice that's a legitimate answer, so I think we're good there. And then the last thing we'll need to check, because notice we can't go any lower than 1 here. If rectangle is 1, that's going to make the x 7, or the circle. And then if this is 7, that makes this 2. So notice in that case there are only 3 options. So notice it doesn't really matter where you start. You just want to start kind of methodically so that you can, you know, rule out any answers that you might have. All right, so lastly, on this page, not 8, each side here would be 10. Okay, so again, I'm going to start with my y just because that's what I'm going to do. So notice still the biggest we could have this be is 4. Think about that for a minute. It can't be 5. Let's go back up to the picture. If this is 5 and this is 5, then that's already 10, leaving nothing for the x. So 4 is the largest thing we can have. If these are 4, that makes this 2. If this is 2, that would make this 8. So it looks like that one's fine. So I'm just going to kind of fill these in. So I want you to pause the video and see if you think any one of those works. If you run into any issues, mark them out. As long as they come out fine, then leave them. So pause the video and then come back to it. All right, so if these are both 3, notice this would be 4, making this 6. If these are both 2, that would make this 6, making this 4. By the way, notice that this column is always double this column. Okay, so it actually means that this has to be an even number, right? And then lastly, if this is 1, that's going to make this 8 and make this 2. So notice we have some pretty strong, clear patterns here, right? Counting up by even numbers, counting down by ones, counting down by even numbers. Okay, so when it makes sense, I want you to show me the work that you have, but for the most part, I just want you kind of thinking about the patterns and thinking algebraically in order to do the homework. So let me show you the homework for Wednesday, if I can locate it here, just to make sure we're all on the same page with what I'm looking for. So it's just the same kind of problems the homework is. So let's kind of look at that together real quick. 1 and 2 are the space blender problems. 3, 4, 5, 6, and 7. So the next 5 questions are some more of those table problems. I want you to list for me all the possibilities. Okay, so not just, you know, the first one you find, I want you to list them all. And then here's what I was talking about. Yeah, I made them pretty tiny. Okay, so if you can't really read all of that, that's not the end of the world. You can just take the larger one that we used in class and kind of use it. So all you really need to be able to see is the 14 pounds here and the 20 pounds here. Okay, for number 9, it's 28 pounds and 34 pounds. So forgive my small font, but I'm trying to actually save y'all some printer ink when you have to print out all the handouts. Okay. Make sure that you're looking on D2L. I've got some instructions about the upcoming test. It's not for a couple of weeks, but on D2L under week 11, I'm listing for you some things I want you to keep in mind for the exam. And then maybe some of you need to respond to me. So make sure you're looking at D2L, make sure you're reading all the emails. And then of course, if you're listening to this, then you're already watching the lecture videos. So I think that's it for the week.